Hello everyone, my name is Fabian Egidy. I am from the University of Würzburg and I am pleased to present to you the work of Christian Glaser and myself about the difficulty of finding optimal proof systems for complex sets. So, first of all, we need to clarify what an optimal proof system is. A proof system, by the definition of Cook and Recco from 1979, is simply a polynomial time computable function. And the statements we can prove in such a proof system is precisely its range. So we say polynomial time computable function is a proof system for its range. To better understand this definition, let's look at an example. So let's say we want to have a proof system for the set containing all propositional tautologies. We abbreviate the set with taut, and then any polynomial time computable function whose range is precisely taut is such a proof system. And here we name this function f. And now f maps all inputs onto tautologies, and this mapping does not necessarily have to be injective. And for a given tautology, all inputs that f maps onto a tautology are proofs of this tautology in f. So here the orange and purple input are proofs for the green tautology. Okay, so this definition, it satisfies all requirements we usually have for proof systems. Here f is complete and correct because f provides proofs for precisely its range, which is precisely taut. So no tautology is without proof, and there are no proofs for anything other than tautologies. And we can efficiently verify proofs because we can use f to check whether a proof is valid, and f is a polynomial time computable function, so this can be done efficiently. Okay, next we want to compare proof systems with each other. And for this, we use the notion of simulation, which compares proof systems based on the lengths of their proofs. We say that a proof system H simulates a proof system G if we can translate any G proof for a statement into an H proof of the same statement. And the translation of the proof increases its length at most by a polynomial. So in other words, when H simulates G, then the proof system G never has significantly shorter proofs than the proof system H. And with this, Krajicek and Putlak defined what an optimal proof system is, and they say a proof system that simulates all proof systems for a set is an optimal proof system. Okay, great. This is the main definition for this talk, and optimal proof systems have many connections to different research areas. To give a brief overview of this, they were initially motivated um, regarding usual open questions in structural complexity theory, like the NP versus co-NP question. But the field expanded and more connections were found. For example, we know of connections to the existence of complete sets for so-called promise classes, or we know of connections to mathematical logics where we can characterize finite versions of Gödel's incompleteness theorems using optimal proof systems. There are connections to the existence of optimal algorithms for problems, to descriptive complexity, learning theory, and much more. So there are plenty of reasons to study optimal proof systems. And one of the first questions one can ask after defining what an optimal proof system is, are there sets with optimal proof systems? And the answer is yes, there are, because all sets in NP have optimal proof systems. But this result is not really that surprising because NP is defined as the class that contains all sets that have polynomially bounded and efficiently verifiable proofs. And since the notion of simulation allows polynomially longer proofs, any polynomially bounded proof system is optimal. So the sets in NP are too easy for the definition of optimal proof systems to make full sense. And because of this, the better question to investigate is, are there sets outside NP with optimal proof systems? And this is one of the long-standing open questions in proof complexity. And here we do not know a single set with this property. But by a result of Messner, we know that there exist sets without optimal proof systems. And as a corollary of this, we know that Cohen-Ehart sets do not have optimal proof systems. But the situation is basically as depicted here. We know that optimal proof systems exist in trivial cases, and that they do not exist for Cohen-Ehart sets, including some sets coming from diagonalizations. So there's a huge number of sets where we do not know whether they have optimal proof systems or not. Now, is this question hard? Intuitively, yes, because this question is being investigated for 35 years and it is still open. But can we make this more precise? Let's have a look at what we know about both possible answers. So if the answer to the question is no, then we already know that proving this, so proving that the answer is no, will be difficult because we know of relativization barriers even when assuming several plausible assumptions. A relativization barrier is a proof barrier. I will explain it in a minute. But what this means is that answering the question in this case is provably difficult because we have to overcome a proof barrier. In the second case, however, if the answer is yes to the question, no such evidence for the difficulty is known. So it could be that finding a set outside NP that has optimal proof systems is feasible with our current proof techniques. And also, both answers are not known to have any unlikely consequences. So it is unclear which answer seems more likely. What this means in total is this question seems intuitively hard, but even after all this time, we do not know whether it is objectively hard because we have no evidence for the hardness in the positive case. Now, this state of research basically raises the following task. Either show that optimal proof systems exist for sets outside NP, or find evidence that answering the question in the positive is also difficult, so that we know that the question as a whole is objectively hard. In our paper, we achieved the second part by also giving a relativization barrier for the positive case, so when the answer is yes. But before I explain our results, I will give a short introduction to the concept of relativization barriers. We can extend the concept of a Turing machine to an oracle Turing machine by giving it an additional oracle tape and access to an oracle, which is just a set of words. And the oracle Turing machine can write down a word on its oracle tape, then query the membership of this word to the oracle and get an answer in one step, whether the word is inside or outside the oracle. And we can use those oracle Turing machines and oracles to come up with a proof barrier. I will explain it using an example. I think every one of you knows that P is a subset of NP. And this proof is very easy. It's just that any non-deterministic polynomial time Turing machine can simulate every step of a deterministic polynomial time Turing machine. And it should also be obvious that this proof also works if we replace Turing machines with oracle Turing machines relative to an arbitrary oracle, because the non-deterministic oracle Turing machines still can simulate all steps of the deterministic oracle Turing machine, including those new query steps. And if a proof method has this property, that it also works if we replace Turing machines by oracle Turing machines with access to an arbitrary oracle, we call it relativizable. Now, it is not special to this proof that it is relativizable, because from 50 years of experience, nearly all known proofs in structural complexity theory are relativizable. There are only very few exceptions, and they have quite specific reasons for this and are not really helpful on a greater scale. So what this means is that currently, when we want to tackle open questions in structural complexity theory, we can do this only with relativizable proof methods. And we can use this experience to come up with a proof barrier. I will show this using an example. So there is an oracle where relative to the oracle, P equals NP. And we get as a corollary of this that any approach to prove that P is not equal to NP must use proof techniques that we currently do not have. Because any proof for P is not equal to NP cannot be relativizable. Otherwise, it would also have to work relative to the oracle A, which cannot be. So from the existence of this oracle A, we know that proving P is not equal to NP is objectively hard because we need proof techniques that we did not develop for 50 years. And we use this approach to show the difficulty of resolving our question. So we constructed two oracles. If we only look at the sets inside P space, this picture shows all that we know about the existence of optimal proof systems. And relative to our oracle, or to our first oracle, the following holds. The polynomial time hierarchy is infinite, and all sets that are in P space but not in NP have no optimal proof system. And this shows that even when assuming an infinite polynomial time hierarchy, we have a relativization barrier for the easiest sets outside NP when we want to show for them that they have optimal proof systems. And this clarifies the situation inside P space, but what about outside P space? And here we have a second oracle with the following property, which we also consider as our main result. Here, NP does not equal co-NP, and all recursively numerable sets that are outside of NQP do not have optimal proof systems. And here NQP stands for non-deterministic quasi-polynomial time, which is just slightly more complex than NP. And as shown on a previous slide, this is what we currently know about the existence of optimal proof systems. And now, relative to our second oracle, nearly all sets outside NP do not have optimal proof systems, and only a small area above NP remains unclear. And so this oracle gives us a relativization barrier for all sufficiently complex sets. Unfortunately, we were not able to achieve a tight boundary like for the first oracle, so there's this small area where optimal proof systems still can exist relative to our oracle. What I also want to point out is that the oracle construction for the second oracle was quite involved because, to give you an idea, we have to consider all recursively numerable sets. And this means that we have to diagonalize against nearly all Turing machines, and those in general do not have any runtime bound, so no bound on their runtime. And so when we construct the oracle, these machines can behave very adversarial because they can suddenly start to accept arbitrarily small inputs at arbitrary moments of the oracle construction, and we somehow have to deal with this. So this is the property in this case, which makes the oracle construction quite challenging. Okay, let's get back to the slide where we consider both answers to our question. Now, due to our oracles, for a positive answer, we also have a relativization barrier that holds for nearly all sets. The first oracle gives one for the easiest sets outside NP, while the second oracle provides this for complex sets. And this explains why no such set was found in the past 35 years, because for nearly all sets, we have to overcome a relativization barrier, and the few remaining sets for which we do not have this, they are in a quite unusual area very close to NP. And it would be interesting to improve our results for this area. So we think that our approach can be used to improve the results for some even slower growing superpolynomial function so that the bound is like even a little bit tighter around NP. But for a tight boundary around NP, we think that new ideas are necessary. Okay, to end this talk, I will give you a sketch of the oracle construction where the polynomial time hierarchy is infinite and no set in P space outside NP has optimal proof systems. This oracle is based on two results. The first one already exists and is a generalization of the famous Karp-Lipton theorem. And it says that if the polynomial time hierarchy is infinite relative to an oracle A, then it is also infinite relative to the marked union of A and any sparse set B. The marked union is just the union of A and B, where we can decide whether an element is from A or B. For example, because we mark the words from A with a leading 0 and the words from B with a leading 1. And with this theorem and some oracle where the polynomial time hierarchy is infinite, we can achieve our desired oracle by constructing one that satisfies the following property, and that is it is sparse and relative to the marked union of a set A where the polynomial time hierarchy is infinite and this sparse set B. P space without NP has no optimal proof systems. And so our goal is to construct such a sparse set B. Okay, we have to prevent that any set outside NP but inside P space has optimal proof systems. And for simplicity, here we restrict to the task of preventing a single proof system F to be optimal for some set L in P space. Because usually we would have to consider all proof systems and all sets from P space and somehow intertwine all construction steps for all pairs of those. But for the sketch, it is enough to just consider one proof system and one set from P space. And now we construct the oracle B as follows. In the first case, if there is a sparse extension of our current oracle such that the range of F is not a subset of L, then we take it. So what this means is if we can add a few words to the oracle and achieve that on some input F outputs an element outside of L, we will do this because this achieves that F is no proof system of L because the range of F is not a subset of L. And this makes progress for our oracle construction because if F is no proof system of L, it cannot be an optimal proof system for L. In the second case, so if this is not possible, then it must hold that for any sparse extension of the oracle, the range of F is a subset of L. And now we make another case distinction. Either the following is possible infinitely often. So if there is a fact y in L and we encode this information, y is inside L into the oracle, and the shortest proof of F for y is longer than some polynomial, then we will do all these encodings in our oracle construction infinitely often. And this achieves that F is not optimal for L, because infinitely often the gap between the length of an encoded word for some fact from L and the shortest F proof for the same element is super polynomial. And we can easily define a proof system that uses the oracle to have short proofs for those infinitely encoded words. And such a proof system can then not be simulated by F. If otherwise such an encoding is only possible finitely often, then this means that at some point of the oracle construction, whenever there is a fact y in L and we encode the information y is inside L into the oracle, F has to develop a polynomially long proof for y. And this gives the impression that by encoding all these facts that are in L, we can achieve polynomially bounded proofs for F, which means that L is inside NP, which also makes progress for our oracle construction because for sets inside NP, we do not have to do anything. But unfortunately, this adds too many words to the oracle such that it is not sparse. Surprisingly, we can show that L is inside NP without encoding anything. And for this, we define a proof system H, which has two inputs. The first input is interpreted as a word, and the second input is interpreted as an encoding for the oracle. And on these inputs, H simulates F on the first input, while assuming that the second input is an encoding inside the oracle. And now H must have polynomially bounded proofs, because if the second input is a correct encoding of some fact y inside L, then F has polynomially bounded proofs, as explained before, because we are in case 2II. And moreover, H cannot output elements outside L, because otherwise F does the same relative to some sparse oracle, which shows that case 1 could have been achieved, which is a contradiction, because again we are in case 2II. So summing up, we either achieve that F is no proof system for L in case 1, or that F is not optimal for L in case 2I, or that L is inside NP in case 2II. And all of this is possible with a sparse oracle. And doing this now for all FP functions and all sets in P space achieves our goal, and in the end, the desired oracle. That's it. Thank you for your attention.